I made a 3-in-1 game console that can play Switch 2, Xbox, and PS5 simultaneously, allowing quick switching between the 3 consoles with the press of a button. They are the 3 major consoles currently dominating the gaming world: PS5, Xbox, and Switch 2. Historically, the 3 companies have been competing in the console wars, resulting in games often not being playable on each other's platforms. So if you want to play a variety of games, you have to buy all 3 and switch between them. This is indeed a decision that aligns with their commercial interests, but for me, it's quite troublesome.
So I decided to combine the 3 consoles into one, creating an ultimate gaming console. I will form Sound Effect as a symbol of trilateral friendship to end the console war.
If you directly bundle the 3 consoles together, it becomes a 19-liter, 10-kilogram big iron block, which is not elegant, so they must be slimmed down. When you open the 3 game consoles, you'll find that the main components are the motherboard, cooling, and power supply. Although the motherboard holds all the electronic components, its physical size is very small. The power supply and cooling system are what actually take up space. So I thought, could the PS5, Xbox, and Switch 2 share the power supply and cooling system to switch back and forth? This way, I could achieve the capability of 3 consoles with the size of 1. The plan is simple. You think it's just about connecting a few wires, 3G LAN with a casing, that simple? How should I design a cooling layout so that all 3 machines can be cooled? Huh? The answer is the Mac Pro trash can, in my opinion, the best looking Mac desktop, and its interior is also very special. The heatsink is in the center, a very sci-fi triangular prism with 3 sides closely attached to 3 motherboards, and the fan at the top draws away the heat. Although Apple bet on the wrong horse with dual GPU technology, leading to no further development for the Mac Pro, it happens to be the perfect blueprint for our 3-in-1 console. After a simple model, I had a preliminary design of a heatsink. Next, I just need to CNC a version in aluminum alloy. 5,000 yuan? Because of the large size, and possibly due to many pits and grooves, the CNC process is particularly complex, so it's very expensive. The same shape, metal 3D printing is also costly, and such outsourced production requires scheduling, which is not conducive to multiple iterations and trial and error. At this point, I made a decision that I later deeply regretted: self-casting plastic columns. Among the many ancient methods of creating metal, there is one technique that is still considered ingenious today, called the lost wax method. In order to create intricately shaped bronzeware, directly carving copper was obviously not very sensible. So the ancients would first carve softer wax, wrap the wax model in clay, and then they only needed to take advantage of the low melting point of wax to burn it away, drying the clay in the process. This cleverly resulted in an empty ceramic mold into which they could pour the molten metal. This cloud-patterned bronze mirror from years ago was made using the lost wax method. Naively, I thought these were all chiseled out by the ancients with hammers. I bought some carving wax and tried to cut a star with it. I would definitely not survive in a survival game. Carving patterns on wax is not suitable for me, but in the year 2025, this might not necessarily require wax. Wax is just easy to shape and has a low melting point. What else can give me a meltable solid? Of course, it's 3D printing. Theoretically, 3D printing is also great for shaping, iterates quickly, and the most common 3D printing material, PLA, has a low melting point and is inexpensive. The most important thing is that I have so many printers on standby. Using PLA, I chose high temperature plaster to make my mold. PLA melts at over 100 degrees, decomposes at 300 degrees, and completely burns at 700 degrees. High temperature plaster can theoretically be heated to 700 degrees without damage. By using the temperature resistance difference between the 2 materials, I can remove the PLA to obtain a clean mold. This method is called the wet PLA method, also known as the wet plastic method. This is my newly printed PLA model. This is the main body of the heatsink. Additionally, I printed this extra piece, which is the channel for the aluminum to flow through. The aluminum will enter here and fill all the fins from the bottom up. The design is from bottom to top to more easily expel the air.
Next, it's time to make the mold using high temperature plaster.
Mix with water, stir quickly, pour into a stainless steel bucket, then put in the PLA model. Before the plaster solidifies, quickly place it in a vacuum chamber to remove the air from the plaster. The entire plaster bubbles like it's boiling. This process is called degassing. After the foaming is complete, wait for the plaster to solidify at room temperature. I didn't expect the plaster to accidentally touch the top of the model, and I have to go through the trouble of digging out this opening. Oh, it's like excavating some artifact. Once it's cleaned out, it can be placed in a high-temperature electric kiln for burnout. This process involves 4 heating stages over 12 hours: drying, pyrolysis, burnout, and finally holding to prepare for the aluminum melt. There is still a lot of ash left inside the mold, and I use high-pressure air to blow away the remaining dust. You can see that the plaster surface captured quite a lot of details from the PLA model, very complete. Wow, the PLA can actually burn so cleanly. That's really interesting.
The next step is melting aluminum. Ventilate, ignite.
A very beautiful blue flame vortex appeared in the furnace. In the dry pot, the aluminum pellets that were placed in advance quickly started to glow red from the bottom and softened. After a short while, they reached the melting point of 660 degrees and completely melted, turning into a silver liquid. At this point, I had to use a very long spoon to skim off the oxides and impurities from the surface of the molten aluminum, just like skimming foam from a hot pot.
It looks funny, but this step is actually very important. Finally, take out the preheated mold, and while both the mold and aluminum are still hot, quickly and carefully pour in the 700-degree aluminum.
I quickly found that halfway through pouring, it wouldn't go in anymore, probably because the aluminum cooled and solidified too quickly, so the latter part couldn't go in. After cooling in water and removing most of the plaster, I achieved my first successful casting. Although it wasn't entirely successful, this result already surprised me quite a bit. The surface is quite smooth, and the edges are also very sharp. Surprisingly, the texture of the 3-dimensional printed support layer is also revealed underneath. Besides the issue of aluminum solidification, there are 2 other problems. First, the heatsink is a bit too dense, and the plaster wall is too thin, starting to crack at the ends. Secondly, the heatsink is parallel to this edge, so this section will be very long. However, these are not major issues. Just adjusting the orientation, thickness, and density of the heatsink should solve them. I realized that when I failed, the advantage of 3-dimensional printing becomes apparent. When the ancients failed, they had to manually carve it all over again. I failed, so I tried again. After readjusting the temperature of the plaster mold and the molten aluminum, this time the aluminum smoothly penetrated the entire mold before solidifying. Once the plaster dissolved in water, the aluminum piece was as perfect as a lotus emerging from water. After sawing off the excess casting gate and polishing, the fins are complete and beautiful. The 2 sides that contact the PlayStation 5 and Xbox motherboard are relatively smooth, but the 3rd side still has a few small pits because there was a little residual gas inside, forming cavities. Fortunately, this side is for the Switch 2, which doesn't need cooling. The aluminum block heatsink casting plan is considered a success. I actually didn't expect it to succeed. The lost wax method is truly the best. Next, use a metal with excellent thermal conductivity, pure copper, to make a plate and then screw it onto the aluminum heatsink. It will evenly distribute the heat generated by the chip across the aluminum surface. The PS5 originally used liquid metal as a thermal medium, but since we have pure copper and a large aluminum alloy, thermal paste will suffice. Next, install the motherboard. Place a 12cm cooling fan under the heatsink, blowing upwards, and then we can power it on and test it. Tower on. Now, Elden Ring has been running here for half an hour, and there's no overheating warning. When measured, this whole area is only 60 degrees, and the heat has indeed transferred well from the chip to the aluminum block. Mission accomplished. Regarding the power supply, initially I thought it was quite complicated and planned to design a 3-position switch to supply power to whichever is in use. But this way has many troubles. You need to shut down the main unit before switching, and the circuitry would be very complex. Until I calculated that although the PS5 has a load of 225 watts, it only uses about 4 watts in standby, which is very energy efficient. The Xbox is similar. Then I don't need to switch. I can just use a 250 watt PC power supply, as long as I don't run 2 games simultaneously. Also, both the PS5 and Xbox Series S motherboards use 12 volt direct current, so they can be connected in parallel. For the Switch 2, just use a transformer with a direct current to USB-C adapter. Speaking of the Switch 2, I have other plans for it.
As a handheld device, it needs to be detachable and portable. So I left the third face of the triangular prism for it and made a new diameter for it.
Base. Actually, the original Switch base wastes quite a lot of space. After removing, only these two things are useful. As for this fan, you all know it's not for cooling the Switch. It doesn't even blow on the console. I understand it's supposed to prevent the heat from the Switch from overheating the dock's motherboard and to cool the dock. We already have a fan at the bottom blowing upwards, so we don't need it. After reducing the weight, the new dock looks like this, a small square box. When opened, there is an L-shaped Type-C extension cable inside, connected to useful electronic components, which will all be placed inside the case. This small square box will be attached to the last side of the cooler, then the Switch will be placed on it. But how do you take it out? I hope it can have a bouncing feel like a toaster, and it can be easy to achieve. Make a platform at the bottom of the box, with a spring installed behind the platform. When I insert the Switch, the platform will be pushed and locked into the hollow of the cover. I just need to press the latch, and the spring will eject the Switch. But the spring's force is too weak. This doesn't even account for the resistance that the C-latch might cause. Later, I repeatedly tried some springs, but none worked well. So, besides metal springs, what other materials also have elasticity? Then I thought of plastic springs, which are quite common in 3D printing. I directly found a 3D printed spring generator on MakerWorld, where you can input values to customize various thicknesses, lengths, and widths without modeling. I generated a whole bunch. Not only can it quickly allow trial and error, but it is also integrated, eliminating the hassle of installation. The entire lower shell spring is integrated, and the upper shell and button are also integrated, requiring no assembly. Once printed, it is a movable button. Moreover, to ensure that the movable part does not stick to the base, two different materials were specially used. The outer shell is PLA, and the spring and push rod are PETG, ensuring the rigidity of the spring.
Using the dual head printing function of the Tazoo HD, the two materials are printed from two separate heads.
Take it off the print bed and it can move. And if you cut it to take a cross section, you can see there's a small design here with the PETG spring embedded directly inside the PLA, so it will never come loose. Next, 3D print a shell and assemble them all together.
First, fix the Xbox motherboard onto the heatsink. The triangular box at the bottom is the power supply box, which contains a gallium nitride power supply. The entire console's power supply relies on it. The small holes around are for air to enter, because a bit above in the middle is the fan compartment. The fan is directly clipped in and fixed there, and it will draw in cool air from below and send it upwards where the main body of our console is placed. Use an L-shaped 3D printed piece to secure the heatsink to the casing, then connect the power supplies of the two consoles and insert the mysterious Arduino and circuit board, which will help us achieve the console switching function. Then fix the electronic components of the Switch dock inside the outer casing and fit the entire casing over it. I also used the laser cutting function of the Tuorju HD to cut two black walnut decorative pieces, installed a light strip here, inserted it, mounted buttons and decorative pieces on the top, and snapped on the base shell of the Switch 2. It lit up. Finally, I attached a metal plate with its name, Nintendo P Xbox 5. Math say
one console. I think it looks better than the PS5. I didn't expect the finished product to be quite bold. Each side has triangular elements. Even here you can feel them. This side is for the PS5, this side is for the Xbox, and the last side is for the Switch 2. Insert the Switch 2. Press the red button to eject it. Now the three consoles share the HDMI cable and power supply. Plug in the power and the front light will turn on. The light is now blue and the screen shows the PS5. Next is the most magical and important button of this console, which is this triangle on top. Press it. The light turns green and the screen changes to Xbox. Press it again. The light turns red and the screen changes to Switch 2. Isn't it super amazing and super convenient? I think it's incredibly convenient. Now let's play some games and see if it can run various games normally. Currently we're playing a Switch 2 exclusive game, Donkey Kong Bonanza, and it's running very well, of course.
It doesn't need cooling. It switches in less than 5 seconds. It's awesome. Playing games on the PS5 is also very normal, unbelievably normal.
At this moment, you suddenly want to play Xbox again, press it once more, and the light turns green. Ah, we have arrived at Xbox!
The Xbox can also run normally. Played for a while. Wow, the vent on this is quite hot. All 3 platforms are running normally on the same console. For a moment I was a bit dazed. Couldn't believe this is real. It feels like a sense of world peace and fulfillment.
The combination of traditional methods and modern technology is surprisingly beautiful. I'm quite satisfied with the final result of this 3-in-1 Ning Tiandu PX Box 5. Initially, I intended it as a joke, but it turned out to be practical and quite good looking. I feel it's not any less attractive than the PS5 itself.
At the same time, it retains the complete functions of the 3 consoles, reduces the size, and makes the wiring simpler. I hope it can continue to serve, reminding people who keep making exclusive games, you just don't want this one. If this project taught me anything, it's not to oversimplify plans.